This video is on forces at angles. I'm Mrs. Estock. Let's get started. To begin our video on forces at angles, let's think about why it's more difficult to hold a weight with your arm stretched out than it is to hold it straight down. So imagine you're holding a heavy weight. Compare holding it down by your side to holding it with your arms stretched out, maybe parallel to the ground. Why is that so much harder to do? Well, it has to do with forces at angles. To help us think this through, we're going to draw some free body diagrams and think about the forces in terms of how big they are and what it means to have a force at an angle. So here's you, smiley face stick figure, and you're holding a weight just down by your side. Arm is not stretched out. You're just letting it holding it straight down. What would the forces be on this object? Well, there's the weight force that's pulling it down, the force of gravity, and it also feels you pulling it up. So maybe an applied force pulling up. And assuming you're holding that weight down by your side at rest, those two forces will be balanced. That way you can hold it at rest, it's in static equilibrium. Now let's say you take that weight and you're doing an exercise maybe and you hold it out to your side. That looks comfortable. What's going on here? Well, you still have to pull up on it, right? And it still has weight to it. So what about this free body diagram has changed? Oh, well, you don't have to just hold it up. Now you also are holding it out, right? Because now your arm is at an angle. You're not only pulling up on the weight, but you're pushing it outward at the same time. So what does that do to the amount of force that you have to apply to the weight overall? You're pushing up and out at the same time. Well, if we add those two force vectors together head to tail, we can see that your arm is actually applying more force because it's the resultant or the hypotenuse of those two forces combined. So the force your arm has to apply when it's out at an angle is bigger mathematically. It's a bigger number value for that force than it would be if it was just being held straight up. You're adding an extra component to that force. That's going to add on to the size of that force. So that's why it's heavier to hold it out to your side than it is to just hold it straight down. We can see this not just with people holding weights, but here's another example of why something at an angle might result in a bigger force overall. Let's say you have to draw in the vector components of the force of an object being held up by two strings. Compare maybe this circular cylindrical object being held up by two strings where the strings are just vertical, it's just hanging straight down. We know there's a tension force holding it upward, but what if we took those strings and we changed the angle of the tension force? So let's say now we're holding that object up with tension forces at an angle. To figure out how big that tension force is, we would draw in the vector components. So in other words, these tension forces are doing two things at once. They're holding the object up and also outward. So there are now two components to that force. There's a vertical component and there's a horizontal component, making the resultant or hypotenuse even bigger. So you're going to put a little more strain on these strings if you attach them at an angle to hold up this object rather than just holding it straight up or down. So what we're seeing here is that the resultant force is larger when it's held at an angle. That's because, again, you're combining two pieces to that overall resultant force. It's no longer just holding it up, it's holding it up and sideways, either left or right. So that added component makes the resultant force bigger. Or another way of saying that, you might have heard in math class, the resultant or hypotenuse is the largest side of that right triangle. So, in order to approach these vector addition questions with forces correctly, we have to think about forces as having both magnitude and direction. So a force is a vector quantity. The length of that force vector arrow tells you its magnitude or how much or how big it is. And then the direction the arrow is pointing tells you the direction the force is pointing in. Well, if you remember, when we do vector addition with any type of vector, not just forces, we have to use the head-to-tail method. So if you have forgotten the head-to-tail method or need a refresher, my suggestion would be to go back and review this head-to-tail method from your notes from projectiles, because we're going to be using the same method in our vector addition of forces at angles problems. So just like we saw with projectiles and breaking a vector at an angle down into components, we're going to be doing the same thing with forces at angles. So when you have a force that's at an angle, it's not only horizontal or vertical, but a combination of those two directions. You have to break it down into its component parts. We're going to treat these two directions separately. So we're going to treat the horizontal direction separately from the vertical direction and create separate net force equations for each direction. So we're working two-dimensionally here. So we're doing double the work. We're solving for net force horizontally as well as vertically. Also, remember from when we did this with projectiles, when you solve for the components, you are replacing the vector at an angle with those component parts. So you're getting rid of the force at an angle. You are not including it in your horizontal or vertical net force. You are replacing it instead with those horizontal and vertical components. And in a moment, we'll work through some practice problems so you can see exactly what I mean by that. How do we calculate the components of a force at an angle? Well, we're using these same equations from the back page of your reference table that we used before when we were doing projectiles and we were solving for the components of velocity vectors at angles. If you're solving for the vertical component, we're using sine. And if we're solving for the horizontal component, we are using cosine. Let's go through a few practice problems to see how these equations are applied to solving physics questions. Let's say that you are tugging on Fido's leash with a force of 60 newtons at an angle of 40 degrees. Well, this is a force at an angle. We're going to need to solve for the horizontal component of this leash pulling force as well as the vertical component. So the 60 Newton force has a component pulling right and also a component pulling up. We can solve for the horizontal component by taking that force at an angle and multiplying it by cosine of the angle, 40 degrees, giving us a horizontal component of about 46 newtons. We can also solve for the vertical component using sine. If I take the resultant force, 60 newtons, multiplied by sine of 40 degrees, I get the vertical component about 39 newtons. So now I have all the sides of my right triangle. I have the horizontal component of the force and also the vertical component of that force. So that's how you solve for the components. Let's take it one step further in this next practice problem to see what you do once you solve for those components. How do we apply them to solving a bigger question like this one? A tow truck is pulling with a force of 5,000 newtons at an angle of 30 degrees above the horizontal on your car. Oh, your car must have broken down. Your car has a mass of 300 kilograms. Neglect friction and draw the free body diagram. Okay, so let's start thinking about the forces being felt by this car. It has weight, so we'll call Fg, that downward force, the weight force or the force due to gravity. The ground is pushing up on the car, so it must have a normal force directed upward. And this tow truck force at an angle has components to it. It's a force at an angle, so we can solve for the horizontal component using cosine, and then we can solve for the vertical component using sine. So of that 5,000 Newton force at an angle of 30 degrees, 4,330 newtons of it is pulling to the right, and 2,500 newtons is pulling up. So now we have a complete free body diagram because we're going to kind of ignore or disregard this force at an angle, the 5,000 newtons, and instead only focus in on forces if they are only horizontal, like the horizontal component, or only vertical. We have three forces in the vertical direction: normal, gravity, and the vertical component. So in other words, we get rid of the one at an angle. We're simplifying things into just two dimensions. So we're focusing it on two dimensions of motion. To solve for the net force in the horizontal or x direction, I have to look at my free body diagram and think, oh, what force or forces are acting in the horizontal direction? And when we look at that diagram, we only see one. There's only one force pointing horizontally, and that's the horizontal component of that tow truck force, which we solved for in the previous slide using cosine. We got 4,330 newtons. Well, if that's the only force acting horizontally, then that is the net force. So we're going to call the net force in the horizontal direction equal to the horizontal component, 4,330 newtons. We can then use that, along with Newton's second law, to solve for the horizontal acceleration of the car. We're using the formula F net equals ma, or A equals F net over m. To solve for A here, we're going to divide both sides by 300 kilograms, and we'll get an acceleration of about 14 meters per second squared, directed to the right, since our net force is directed to the right. Remember, the net force and the acceleration will always point in the same direction. Now let's solve for the net force in the vertical or y direction. This time, we have more than one force in the vertical direction. When we look at our free body diagram, we have three forces in the vertical direction: the normal force and the vertical component of the tow truck force are both directed upward, and the force of gravity is directed downward. If we think about how these forces have to add together to give us the overall net force, think about the acceleration of this car. In the vertical direction, is this car accelerating up or down like an elevator? No, it's probably vertically remaining at rest on the ground. So, if the acceleration is 0 in the vertical direction and F net equals ma, if we plug in 0 for acceleration, that means the net force has to equal 0. So in the vertical direction, this car is in equilibrium. In other words, if I add together these three forces, considering their directions, so the vertical component and the normal force are both positive. I'm calling up my positive direction. And the force of gravity is downward, so I made that negative when taking the sum of all of those vertical force vectors. I know that when I add all three of those vectors together, they all have to balance each other out to equal 0 newtons. We can use this net force equation to figure out the normal force acting on the car. This is one of those examples where the normal force is not going to be equal to the force of gravity, and that's because we have 3 vertical forces here and not just 2. We're solving for the normal force. If we simplify this equation so that the normal force is all by itself on one side of the equal sign, we get that the normal force will be equal to the force of gravity minus the vertical component of the tow truck force. I can solve for Fg by taking mass times 9.81 meters per second squared. And we've already solved for the vertical component of the tow truck force. We used sine to do that in a previous slide. That was 2,500 newtons. So overall, the normal force is going to be equal to 443 newtons directed upward. That is it for forces at angles.